Hi everyone, in this video we're going to talk about graphs of logarithmic functions. First we're going to recall that the logarithmic function with base a is the inverse of the exponential function with base a. And remember that we learned that graphs of inverse functions are symmetric with respect to the line y equals x. We already learned about graphs of exponential functions. For example, this is the graph of the exponential function y equals 2 to the power x. And to obtain the graph, we found and plotted the following 7 points. And if I take these ordered pairs and interchange x and y values, I'm going to obtain points that belong to the graph of the inverse function. In other words, the logarithmic function y equals logarithm of x with base 2. Let's plot these points and see how the graph is going to look like. Here's what I got. This is the graph of the function y equals logarithm of x with base 2. And I can see how the graphs of these two functions, which are the inverses of each other, are symmetric with respect to the line y equals x. So what can we say about the logarithmic function based on its graph? First of all, the graph is increasing. I can see that the x-intercept is 1, 0. This graph crosses the x-axis at 1. I can also see that while the graph of the exponential function has its horizontal asymptote at the x-axis, the graph of the logarithmic function has its asymptote at the y-axis. So this graph is never going to cross or touch the y-axis. And that's because x values of the logarithmic function represent the result of taking base 2 and raising it to the power y. No matter what power we use, 2 to the power is never going to be 0 or anything negative. So we can say that the y-axis is the asymptote of this graph as x approaches 0 from the right. And that means that the domain of this logarithmic function is the interval from 0 to infinity. And 0 itself is not included in that interval. How about the range? What can we say about all possible y values for this function? Since this graph goes up without any bound and down without any bound, the range of this function includes all real numbers. While graphing the logarithmic function as the inverse of the exponential function, of course, is not the only way. Let's graph this logarithmic function by finding and plotting points. Our function is y equals logarithm of x with base 1/2. Typically, we start by selecting various x values and placing them in the first column, and then use the second column to calculate the corresponding y values. However, if we look at this function, we'll see that selecting the x values is not very convenient. Remember, x that stands inside the logarithm represents the result of raising 1/2 to the power y. Selecting result and trying to figure out the power is not very convenient. A better approach to setting up the table of values for a logarithmic function is to rewrite the logarithmic function using an equivalent exponential form. In other words, it's going to be base 1/2 raised to the power y equals x. And instead of selecting the x values, we're going to start by selecting y values of this function. After all, it doesn't matter which variable we start with. Let's select these values of y, which again represent the power of 1/2. And in the second column, we're going to find the corresponding x values by taking 1/2 and raising it to each value of y. So first, it's going to be 1/2 to the power -3. To evaluate this expression, I need to change power from negative to positive. For that, I have to take the reciprocal of the fraction. That's going to be 2 over 1 to the power 3. That's same as 2 to the power 3, and that's 8. And now be careful. So what is the first point that we found? Remember, when we write down an ordered pair, we always have to put x first and then y. So the first point is 8, -3. Okay, so I found 2 more points. Therefore, -2 and 2, -1. When y equals 0, x equals 1/2 to the power 0. And that's always 1. So the corresponding point is 1, 0. When y equals 1, 2, and 3, the corresponding x values are 1/2, 1/4, and 1/8. Well, let's plot all these points. Here they are. I can see how I'll connect them, and I notice that the line will be getting close to the y-axis, but I know that it will never touch or cross the y-axis. For the same reason that we just talked about, x represents the result of raising 1/2 to certain power. No matter what power we choose, no matter what y value we pick, this expression will never be equal to 0 or anything negative. So this is how the graph is going to look like. And the y-axis will be its asymptote. It's the vertical asymptote of the graph as x approaches 0 from the right. I noticed that this graph is decreasing compared to the previous one, but that's because the base of this logarithm is less than 1, or I should say between 0 and 1. So the graph of a logarithmic function will be decreasing every time when base is between 0 and 1, and increasing when base is greater than 1. When it comes to the domain and the range of the given function, it's going to be the same as when the base was 2. Domain, or all possible x values, are an interval from 0 to infinity, and the range, or the possible y values, include all real numbers. That's the interval from negative infinity to positive infinity. And one last observation here is the x-intercept. Remember that the x-intercept of the graph of the logarithmic function with base 2 was 1, 0. Well, the x-intercept of this function, logarithmic function with base 1/2, is also 1, 0. And in general, all graphs of basic logarithmic functions, no matter what base is, go through the point 1, 0. That's because the y-coordinate of that point, which is 0, represents the power to which we raise base. And as a result, we're always going to get 1, which is the x-coordinate. And finally, let's observe some other behavior of the graph of a logarithmic function. Here we have two examples. Notice that in both examples, the base of the logarithm is 2. However, in the first case, 1 is being subtracted from x. And in the second case, 1 is being subtracted from the entire basic logarithmic function. How will that affect the graphs? Well, when a number is being subtracted or added right next to x, that indicates the horizontal shift of the basic function. In particular, to obtain the graph of the given logarithmic function, we can take the graph of the basic function, logarithm of x with base 2, and shift it 1 unit to the right. The horizontal shift or translation is always opposite to the sign in the front of the number. -1 means shift to the right. And here is the graph. When we shifted the graph, its vertical asymptote shifted along with it. And now it's at x equals 1, which means that the domain of this function is from 1 to infinity. And the range stays the same, all real numbers. When a number being subtracted from or added to a basic function, that indicates vertical shift or vertical translation. And here things are straightforward. If we subtract 1 from the basic function, it means that if we shift its graph 1 unit down, we're going to obtain a graph of the given function. As you can see, it no longer has its x-intercept at 1, 0. However, the domain and range will stay the same as for the basic function. So these are some of the facts that we can learn about graphs of logarithmic functions.